Hi, now we have a new section, 11.3, the model search. In multiple linear regression, the one hot issue is how to choose the predictors. So suppose the y is fixed, but we have the many candidates of predictors, x1, x2, up to x100. And often it's not realistic to include all 100 variables. And also, the sum of the variables are not useful to predict y. Possibly, maybe all variables are related to y, but sometimes when we have x1 and x2 in the model, we don't need x3 anymore. So that is often the case. So what's the best set of predictors? So that is the theme of this section. And conceptually, we have the two objectives. So one is the best model for prediction. So how to best predict y. And the next one is the true predictors. What's the true model? So it sounds two are almost the same, but it's slightly different. Because the best model for prediction is usually larger than the true model. So suppose that y is explained by x1, x2, x3, x4. Okay, so x1 has very large contribution, and clearly it's useful to predict y. And x2, x3, x4, okay, so suppose these are not significant. Each of these are not significant, but in total, these three variables seems significant to predict y. Then what's the best model? Just y on x1 or y on x1, x2, x3, x4? Suppose x2 and x3 and x4 have almost the same contribution to y. And it's not clear. Sometimes x2 is truly in the model, and x3 and x4, just by chance, it looks significant to predict y. But anyway, so we don't have such information. In such a case, probably we would just in case like to include these three variables. But if you wanna predict the true model, if you wanna get the true model, then maybe you wanna only take x1 and we just discard x2, x3, x4. So generally, prediction model includes more variables just in case that those information are useful. Yeah. So here the objective is the best model for prediction in this section. And so some basic thought. And to select the best model, basically we have two ways. So one is the more kind of labor-intensive or computer-intensive method. So if we have p candidates of predictors, we try the 2 to the power p combination. So typically, if p is less than 10, it's the doable because the 2 to the power 10 is 1024, and running 1000 model is usually feasible in today's world. But if p is 30, it's hard to check everything. So if you have a supercomputer, it may be possible, but okay, suppose it becomes 40, then it becomes impossible. In such a case, we use the stepwise procedure. So we have the two patterns and actually the mixture of it. And the first pattern is we start with the smallest model, y is equal to beta naught. Then add best additional variable until best model is obtained. So we have 100 candidates of predictors. So next model may be y is equal to beta naught plus maybe beta 31 times x31. So we try the beta naught plus beta 1x1, beta naught plus beta 2x2, and up to beta 100x100. So we have to try 100 models, and we choose the best model. Then next, we choose additional predictor. What is the second best predictor? Then maybe x5 is the best, then we choose this model. But at some point, even if we add one more variable, the model does not become better. So then we stop at that point. So still we have to try many cases. So in the case of 100 possible predictors, at first we try 100 times, 100 patterns. And next time we have 99 remaining variables. So 99. Next time 98 until the model stops. So unlucky case, maybe all variables are finally useful. In such a case, we have to try these times. But the number of models we have to try is just a summation of 1 to 100. So that is 5050. So that is much, much smaller than 2 to the power 100. So it makes sense. And 5,000 times models is not really unrealistic in today's world. And another method is starting with the full model, then remove the variable with smallest contribution. So that is backwards deletion. So we fit the full model first, then we drop the least important variable. Yeah. Then until the best model is obtained, then we only retain the necessary variables. Right? Or we can combine two. So each time we add one variable or we delete one variable, then we move around to search for the best model. So basically these methods these methods are not guaranteed to reach the best model. For example, we may include the x1 first, then x2 first, then x3 will never be adapted. But sometimes, sometimes it can skip the the best model. Yeah, for example, x1 is selected first and x2 is selected second and x3 is selected third. But if we combine x2 and x3, then we can perfectly explain why, and x1 is not necessary. So that is possible, right? So one variable is not as strong as x1, but if we combine two, then it's much better than x1. So in such a case, we have to remove x1. But for example, the forward selection cannot remove it. A similar situation happens to the second case, and in very complicated situation, also the third one is not guaranteed to reach the maximum, since we haven't tried the all combinations. But most of the time, so either of these methods, they can reach the optimal model. Also, another consideration is which is faster, the first method, forward selection, or backward deletion. Maybe it's hard to imagine at this point for you, but actually the forward selection is much faster in many of the cases, because the backward deletion, we start with the large model. If we have 100 variables, then we have to calculate the inverse matrix of 101 by 101. So it's a huge matrix, so it takes time to calculate. Forward selection, since we start with a smaller model, and a smaller model we can fit very quickly, so actually the amount of computation is much less. So forward selection, much less calculation. So you can try forward selection first. Yeah, so these are the basic concepts to find the best model. Okay, so the next question is, okay, even we decided the algorithm, what's the criterion for the selection, the first variable, we choose the first variable, what's the criterion to choose that first variable? Also, more importantly, that if we add one more variable, then residual size gets always smaller. But since the contribution of the additional variable is too small, then we decide not to add variable. So what's the criterion not to choose variable? So we need some legitimate criterion. And usually we don't use adjusted R-square. So adjusted R-square certainly penalize a large model, but this model tends to choose too many variables. So I cannot explain mathematically, but usually when we use adjusted R-square, it chooses too many variables than the best prediction model. So usually we use AIC if the theory is well developed. So Akaike information criterion. So this chooses the optimal set of predictors for prediction, and the criterion is to minimize the 2p times negative 2 times the log likelihood. So L is the likelihood function of the model, and the p is the number of predictors. So actually, if we have predictor x1 to xp, actually we have intercepts, so the p becomes p plus 1, but basically this is the number of predictors. Yeah, so okay, so 2p, and we minimize this criterion. So the p is large, so certainly this AIC penalize the situation, because more predictors we can explain more, so that is trivial. So the larger model, we have to penalize larger model, so we have to have a kind of smaller p. But the likelihood, larger is better. So negative likelihood, smaller, negative likelihood, the smaller is better. So if we have more variables, then we can have larger likelihood and a smaller negative 2 times log likelihood. So basically this balance the model complexity and the model performance. So if smaller model performs well, then we choose that. And the another criterion is cross-validation. So cross-validation is the basically the simulation method. So suppose that we have the data set, and the data set, and we randomly divide data set into several pieces, such as D1, D2, D3. Then at first, we fit the model with D1 and D2. So suppose we have the model y is equal to beta naught plus beta 1 x1 plus beta 10 x10. So then we fit the model with these two data sets, then test that estimated model with the remaining part of the data, D3. And in such a case, maybe we only use D3 to test. So we have more uncertainty. So we try the another way. So use D1 and D3, then test with D2. And also use D2 and D3 to fit the data and test with D1. And we combine and we take the sum of the squared errors for all three simulations. Then we can get a kind of, we can, mimic the situation of doing prediction for out of sample, new data set. And this AIC and cross-validation are basically guaranteed to achieve the best prediction performance for very large N. And some other criterion also exist, such as the Schwarz, the Bayesian information criterion. So it chooses slightly smaller the model than AIC and cross-validation. Yeah, and these days, which is more often used? Actually, the cross-validation is more used because the AIC can be used only when likelihood is known. So linear model, it's fine, but it's very complicated model. We don't have likelihood function. So neural network, theoretically, we can have likelihood function, but it's harder. So the cross-validation, always we can simulate it, so it's better. Likelihood function, we need some theory behind the model. So if there is a theory, it's more effective, but if not, it's hard to calculate. So it's interesting. Cross-validation, more computer intensive, and AIC, the more human intensive, in the sense that we have to develop a theory to calculate likelihood. And often the human power is the bottleneck to do something